Okay, everybody, welcome to this morning session. So we start today with Irene Valenzuela, who's going to talk about the CFT distance conjecture and non-critical strings. So please.
No, I did it. Okay, good. First thing in the morning. So, well, thank you very much. Thank you to the organizers for putting together the conference and the invitation to speak. And thank you to everyone here for waking up early and being the first talk after the conference dinner. Especially thank you to all of you that came also at 9:30 because didn't check the schedule like me. I sympathize. That's even more motivation. So very much appreciated. Okay, so to start the session today, I'm going to tell you about the status of the distance conjecture in CFTs and how it gets related to the appearance of non-critical strings. So this is based, well, it started with this paper years ago with Eric, Leonardo, and Comron, but I want to tell you about recent progress and with José Calderón Infante and ongoing new results regarding these non-critical strings that we are working on right now. Okay, so to start, let me very quickly, or well, not so quickly, review what is the distance conjecture in the Swampland program. So first in the gravitational context before moving to CFTs. So the idea is that if you have an effective field theory weakly coupled to Einstein gravity with a bunch of scalar fields like appears here, the vacuum expectation value of these scalar fields parameterize what is known the moduli space, okay, the scalar field space of the theory. And when these EFTs arise from string theory, there is a very typical feature that we learn, which is that different regions of the moduli space are described by different perturbative descriptions of the theory, which are related by dualities. Okay, it's one of the first things we learn in string theory. And this implies that when we move to different regions, the degrees of freedom that are light and become fundamental are different. And this happens in a very particular way. Okay, so we can quantify a bit better what it means moving in the moduli space by defining a distance. So there is a very natural metric in the moduli space, which is just given by the field metric of the kinetic term of the scalars. And then you can define geodesic distance using this metric, so that whenever we go deeper in the perturbative regimes, which happen to be at infinite distance, using this definition, there are new degrees of freedom that become light, and this happens in a particular way in the sense that the mass of these degrees of freedom becomes light exponentially in terms of this distance. Okay, so if you have some example like type 2b on a circle, you have at large radius, you have the Kaluza-Klein tower of states becoming light. So that tells you that the theory actually contains extra dimensions. But if you go to small radius, you have winding modes now becoming light. And we know that there is a dual description. So they behave as Kaluza-Klein modes in type 2a. So that's the new perturbative description that takes over in that region of the moduli space. Okay, and this always happens in this way. So the distance conjecture is just promoting this feature to a universal constraint and saying that whenever you go to infinite distance in the moduli space, you should always find an infinite tower of states becoming exponentially light in Planck units when approaching any of these infinite distance boundaries. Okay? Good. So this is interesting because it gives us information about when and how Einstein gravity breaks down. Okay, so whenever we find these towers like string modes, Kaluza-Klein modes, I mean, the QFT we had is not valid anymore, right? So it gives information about the quantum gravity completion that takes over and what is the nature of that theory, like whether it contains strings or extra dimensions or what's going on. So that can have also phenomenological implications. So the distance conjecture plays a central role in the swampland program because it's related to many other constraints. So if you want to start proving this swampland conjecture, this is a good starting point because it has many implications, like many ramifications, and also phenomenological implications. So that's why there has been many works in the past year testing this in the context of string compactifications to Minkowski space, okay, where we have supersymmetric moduli spaces and we can control what's going on in different corners. And there are many things I could tell you about this, like there are many interesting patterns, relations we have found, but the important one for this talk, one of the lessons we extracted by doing this, is that the exponential decay rate, so we say that the mass always becomes exponentially in terms of the distance. So this exponential rate originally was like some random order 1 parameter. It's not random anymore. Okay, so this exponential rate is very constrained, and it depends on the microscopic nature of the tower. So from string compactifications to flat space, we found that so far it seems it always satisfies these bounds, which are saturated either by the critical string, oscillator modes of the critical string, or a Kaluza-Klein tower of the compactifying 1 dimension. Okay, so I would argue that this is one, if not the most universal feature that we observe in string compactifications. But the question is, can we really prove that it's a universal feature of quantum gravity, or is it just based on the examples that we have? No? How can we try to understand why this is happening, or if it's always going to happen, or just depends on the classes of compactification that we are used to work with? No? Like, okay, we know it works in Calabi-Yau compactification, toroidal compactifications, but it's very difficult to get a proof this way, right? Because we don't have an exhaustive classification of the string landscape. So how we know that we are not missing something, right? So what I want to talk about today is, okay, this is difficult to do, but in the context of ADS, like if we now consider ADS backgrounds, we can translate this feature to a statement on the CFT, and then try to prove it universally. And not just based on examples. Okay, so try to use CFT techniques to prove or disprove this statement as a universal constraint of quantum gravity in ADS. So I thought it fits for this audience because here I could imagine that many of you are more familiar with holography than different Calabi-Yau compactifications. For me, it's the other way around, so I'm also now exploring this new landscape. But we'll see that we are actually going to learn new things about CFTs. So let's translate it. So the point is, this moduli space I was talking about, no, the scalar field space, gets translated on the CFT to the conformal manifold, to the space of exactly marginal couplings. And the notion of distance, no, this field that comes from this field metric of the kinetic term, just gets translated to the Samolnikov distance, which is measured by the metric coming from the 2-point function of the marginal operators. Okay, so if you translate this distance conjecture to CFTs, it implies that when you have some local unitary CFT, because I still want to have some gravitational dual, with a conformal manifold, then there should be an infinite tower of primary operators saturating the unitarity bound. That will be the equivalent of saying that they become light in the bulk. At every infinite distance limit measured by the Samolnikov metric, in such a way that the anomalous dimension of these operators, which is the difference between the scaling dimension and the unitarity bound, scales exponentially, decreases exponentially in terms of this Samolnikov distance. Okay? So this is the statement. I wait a bit so you can think about it. So we should have an infinite tower of operators saturating unitarity bound at every infinite distance limit. And now you can try to see whether it's always realized or not. So, well, we formulated this in this paper for dimension bigger than 2 for the CFT, but similar ideas actually had already appeared in 2 dimensions in these previous papers. And okay, so let's try to do something with this now. So what do we gain by considering now the distance conjecture in area CFT? Well, there are 2 things. First, as I was saying, we can try to prove the swampland distance conjecture using CFT techniques in general. For this, ideally, we would like to show a one-to-one correspondence between the infinite distance limits in the Samorgikov distance and the existence of this infinite tower of operators saturating the unitarity bound. So since we formulated this a few years ago, there have also actually been already 2 papers proving one of these directions in complete generality, like not based on examples, just using the CFTs local and unitary. So this was first paper by Floran and Jose in dimension bigger than 2 CFTs without even assuming supersymmetry. That they saw that when the higher spin gap goes to 0, that's at infinite distance. And more recently by Hiroshi and Jifan for the case of the scalar gap in 2 dimensions. So that direction is already proven and it's left. So the other direction, it's the most tricky one, is not proven yet. It's supported by all the examples, all known CFTs that we have. And we are working on that. Okay, so now there are different people trying to think on this direction, and if you know me, I'm an optimistic person, so I really hope we will be able to report on this at some point and really have a proof of this, but we'll see. So that's the status right now. The message I want to give, I'm not going to talk more about this, but the message I want you to keep also is that it was at least surprising to me that this seems to work in all examples. When I say all examples, I mean any CFT, local and unitary. I'm not requiring that it's a holographic CFT, even, that in the sense that has a large N and large gap. So it even works, I mean, even if this distance conjecture started as a constraint for Einstein gravity theories that we observe in string compactifications, it seems to work even if the gravitational dual is non-Einstein. So it really suggests that it's some universal feature of quantum gravity in ADS. But okay, we'll see. We still have to prove this part. Okay, so the second thing that we gain by translating this to ADS CFT is that, I mean, not only we can use CFT techniques to learn about swampland, but sometimes we can also use swampland insights to learn about CFTs. So in the rest of this talk, what I want to do is actually follow this path in the sense that we are going to start a classification of infinite distance limits in 4D conformal manifolds to see what are the, in practice, what are the towers of operators that we obtain, what do they correspond to, and this will lead us to some classification of the possible tensionless string limits that you can have in these conformal manifolds. So in the gravitational dual implies that some string becomes tensionless, and sometimes we'll see that they correspond to the critical string or more exotic non-critical string backgrounds. Okay. So the question is, yeah, which free strings we can have? No, what is the quantum gravity completions that we have in general for CFTs? Okay, so before starting with this classification, let me make some comments about what is the expected nature of the tower of operators or of states. So let me distinguish between the flat space case and ADS. So in the case of flat space, all these works checking the distance conjecture in different compactifications show that in practice, the tower in the end, it always corresponds in some appropriate dual frame to a Kaluza-Klein tower or oscillator modes of the critical string. This is more constraining than it looks because in string theory you have many different types of objects, okay? And many times when you go to the infinite distance limit, you get, I don't know, like some wrapping brane and some cycles that are the lightest tower. But the whole point is that whenever that happens, you can always find some duality frame in which these wrapping branes behave either as a Kaluza-Klein tower, and that's it, like the D0 branes are Kaluza-Klein tower of M theory, or as the critical string, like if I have an NS5 brane wrapping some 4 cycle, depending on the nature of this 4 cycle, then that actually corresponds to the critical heterotic string. Okay, so these are the possibilities, which tells you that in these cases, yeah, it's always the quantum gravity completion. It's always like a string theory, or and includes extra dimensions. Now, what happens in ADS? Okay, from the perspective of the CFT. So here it seems different, the situation, depending on whether I am in 2 or 4 dimensions for the CFT. So in the case of 2 dimensions, it's about scalar operators, the story. In 4 dimensions, seems to be about higher spin operators. You could ask, okay, what about other dimensions? So the point is that dimension bigger than 4, we only have isolated CFTs. We don't have conformal manifolds. And in dimension equals 3, the examples are typically compact. Okay, so if we want to consider infinite distance limits, then the CFTs that we know that have infinite distance limits are 4 dimensional. And there's still the question of whether one can show that 3D are always compact or not. Okay, so in this talk, I'm going to focus actually on D equals 4, okay? And the question is, okay, I'm gonna show how these higher spin operators appear, and we are gonna try to understand what do they correspond to in the bulk. Is it always the critical string as happens in flat space, or can we get more exotic things? Sorry, this is the same. Yeah, okay, so let's focus on 4D CFTs. So with any level of supersymmetry. So now I want to take this landscape of CFTs, like known CFTs, and study what are the possibilities. So the infinite distance limits that are known in these cases, they always correspond to weak coupling limits, in the sense that there is a gauge coupling of the CFT, gauge theory that goes to 0. And so there is a subsector of the CFT that becomes free. Now it's easy to see why these free limits are at infinite distance, because, well, these are complex conformal manifolds. So the gauge coupling is part of this complex marginal coupling. And when we are at weak coupling, the marginal operator is just trace of F squared. So we can compute the 2-point function to obtain the Samorgikov metric. And just because this is the perturbative limit, it always takes this hyperbolic behavior, so that when you compute the distance using this metric, you find that the weak coupling limit is at infinite distance in the conformal manifold. Okay? Good. Now, the point is that when we have a free sector, it was shown by Mandelstam and Sivoedov that that's equivalent to having a higher spin symmetry, in the sense that we have infinitely many a continuum of higher spin operators saturating the unitarity bound. So you have the conserved higher spin currents. So you can see what's going on now. So whenever we have these weak coupling limits, they are at infinite distance, but also they have these higher spin operators that saturate the unitarity bound. And moreover, one can show, just because this is a perturbative regime, that the anomalous dimension goes as the gauge coupling square. So in terms of the distance, indeed behaves exponentially with the Samorgikov distance, so the CFT distance conjecture is realized in all these cases. And not only is realized, but we can be very quantitative about how the mass, well, anomalous dimension here goes to 0, what are the exponential rates. So, for example, if we think that we have some large n CFT, we can translate this to the mass of some states in the bulk. And then when writing the mass in Planck units, just to relate to the usual distance conjecture, then the exponential rate goes as the square root of 2 times the central charge of the theory over the dimension of the gauge group that gets free. And that's universal for any of these weak coupling limits. Okay. So first observation is that indeed this has a lower bound, because the dimension of the gauge group cannot be larger than the central charge. So there's a lower bound on how light the states become, which give you an upper bound on the cutoff of the theory. So you know that at the very least you should find states at a given scale. So that's interesting. Okay, so yes. So here we are moving the conformal manifold of a CFT, so for fixed central charge. So it's the total, like, you mean which central charge? Yeah, C and A. So I'm talking about C, like for, okay. A will appear later. Good. No, the free theory, it's in the strict limit. This is like when approaching the limit, so it's becoming free, but it's not exactly free yet. It's perturbative, it's like a perturbative gauge theory. The value of C? No, because I'm moving the conformal manifold, so C is fixed. Yeah, exactly. Okay. Yeah, yes, it's the same, just mean it's the same data at the free point, any points, yeah. Okay, good. Okay, so this is the general result for the exponential rate. So what do the higher spin states correspond to in the bulk? So let me just first show it in the canonical example, right, of n equals 4 super Yang. So here, of course, when the gauge coupling goes to 0, what's going on is that we are sending GS in the bulk to 0, right? And then what happens is that indeed the fundamental string is becoming tensionless in Planck units, right? Because the ratio between the string scale and the Planck scale is controlled by GS. So this weak coupling limit of the CFT indeed corresponds to a tensionless limit of the type 2B string in the bulk. And the higher spin tower of operators map to the oscillator modes of the critical string. Okay. Good. So the exponential rate, you can compute it for n equals 4 super Yang means is 1 over square root of 2. And just one side comment. You can ask me about this later if you are interested, but just want to remark that it's important to keep in mind that this result is valid in the perturbative regime of the CFT. So this is small TOF coupling. It can be connected to the supergravity result that we would obtain at large TOF coupling. And we actually do this carefully in the paper with Jose using integrability results. And there's a very nice connection between the two as you change the value of the TOF coupling in such a way that the bounds I showed you at the beginning coming from the Swampland are satisfied. And in a spin-off, we can also use this to give some argument for ideal scale separation, but that would be a different topic, so ask me about this later if you're interested. Because you change n. Here, what you are doing is to change what is the rate. So n goes to infinity, the gauge coupling goes to 0, but they can go with different rates. Like the ratio is different, depending on the value of the TOF coupling. And the point is that when you go to large, so the quantization of the string is different if you are in the background in which the curvatures are very large, or you are in the background in which you are the perturbative regime of the CFT, so the curvature is for the radius. So this is, okay, so this is the alpha, so this would need more time to explain, so I can show you later. This is the alpha in the conformal manifold. Okay, this would be like the alpha taking into account both directions. So it depends which limit, which trajectory we are taking. So it becomes more like path, depends on the path. But you can follow for any path and see how it changes depending on which path you take. Here would be only moving the conformal manifold, here we're moving in a different trajectory, but I can show you later. Okay, so just wanted to say, so n equals 4 super mil is clear that this limit is the tensionless string limit of the critical string, but what about other for the CFTs? Okay, so what are the possible values of the exponential rate, and what does the higher spin tower correspond to? Okay, is it always the critical string, or can we get other things? So to start, let me see. Okay, to start the classification, in these papers, we restrict our attention first to 4 CFTs with large n, because I'm interested in understanding the bulk dual, even if it's not Einstein, but it's still at least having some gravitational weakly coupled theory. And then we restrict the attention to gauge theories that have a simple factor. So I only have one gauge coupling. It's just to simplify my life. It's not the whole thing, but it's the first starting point to start considering more general cases with several gauge coupling and different type of limits. Okay. So if you restrict to this case, there is actually a full classification of the possible CFTs you can have with a simple gauge factor. So we are going to the weak coupling, so that's why in this limit they become Lagrangian, right? Because the gauge coupling is going to 0. And this is the possible theories you have with the values of the central charges and so on. This is written in n=1 language, but here you have both n=1 and n=2 theories. The point is that I divided all these theories in 3 tables, which correspond to the 3 values that you get for alpha in this landscape of CFTs. Okay, so in other words, you take all CFTs, 40 CFTs with large n and a simple factor of the gauge group, and you only obtain these 3 possible values of the exponential rate for the higher spin tower. And as you see, it doesn't depend on what is the gauge group. Here you have SUN, USP, and SON, and so on. And it doesn't depend on whether it's n=1 or n=2. It's like different thing, okay? So you might wonder, okay, what's special, right, about these 3 classes? What distinguishes them, right? Why we have these 3 values? What do they correspond to? So in this case, since we only have one gauge factor, okay, we can write this exponential rate purely in terms of the central charges of the CFT, so both A and C. And this happens to be, I mean, the alpha depends only on the ratio between A and C. So these 3 values happen because for this landscape, for this mini landscape of CFTs, it happens that there are only 3 values for the ratio of A over C. The first one is precisely the holographic CFTs, right? So A is equal C. So this will be dual to Einstein theories. And this is indeed the value that we have in n=4 super-Young Mills that corresponds to the critical type 2B string. So the first class is just, I mean, this higher spin tower will just correspond to oscillator modes of the critical string in all these Einstein theories. So in other words, all Einstein theories that have A = C have the same higher spin tower, which is just the critical string. Okay. What about the others? Okay. These are not holographic in the sense that even if I have a large n limit, A is different from C, so there will be higher derivative corrections that are not suppressed because typically you don't have a large gap. Okay. So what are these higher spin states? Okay. So the Swan plan inside is that from checking this in many compactifications, as I said, we learned that the value of alpha give us information about the microscopic nature of the tower. So this suggests that these 3 values correspond to 3 different towers of oscillator string modes. Okay, so 3 different types of tensionless string limits. So we can kind of classify all the CFTs in categories depending on what is the tensionless string limit that we have. So what is the dual string background? And the goal is to check, okay, whether this is indeed the case, like whether they correspond to string and what is that string, no? So how much time I have? It's 28, okay, 5 minutes. Okay, good. So we did 2 things. First, we compute the thermal partition function, the 3 sphere at the free limit for all these CFTs. So including any content of matter, any value of the gauge group, to show that indeed they all exhibit a Hagedorn-like density of states. But indeed, when we compute the Hagedorn temperature, it's different for each of these 3 classes. And then we give some universal result for the Hagedorn temperature that depends purely on the value of alpha, or equivalently in the value of the ratio between A and C. So that we have a different Hagedorn temperature for each of these 3 types of CFTs. So this suggests that indeed they correspond to some stringy-like object. But we want to do more, okay? We want to understand whether we can infer what is this object in the bulk. So As I said, the first one is just the critical string, but the other ones, they take place in non-Einstein theory, so are difficult to analyze from the bulk. But something we can do, and with this I will finish the talk, is that we can construct some interpolating models that, starting from some holographic CFT that we know what is the bulk dual, we can take some limit and obtain these other non-holographic ones and follow the limits to see what this string corresponds to. Okay, so this is idea that we actually borrow from this paper, for example, of Gary Pomon and Rastelli, which they did this for this particular theory, which is n equals 2 super QCD. And what we are doing is to do this for all the others. Okay, so very quickly here I had like some summary of what they did in this particular example, because it's a canonical example. Maybe I will go quickly because I don't want to run out of time. So in this paper, they can show that n equals 2 super QCD. You can construct it from an interpolating model, starting from SUN cross SUN, taking one of the gauge couplings to 0 while the other is fixed. So that decouples, and what is left is this n equals 2 super QCD. So if you know the brain picture and the gravity dual on this side, now you can follow this limit here and see what you get here. Okay, what is the dual? So may skip this. The point is that you can, in this case, you have DC brains on an A1 singularity, so you can dualize this to have this elliptic model in which you have 2 NS5 brains and D4 brains between them. And this limit here, this Wick-Coupling limit, corresponds to a double scaling limit in which you approach the 2 NS5 at the same time that GS goes to 0, such that the ratio between the two gets fixed. Okay, so that's equivalent to sending only one of the gauge couplings to 0. And therefore, what is left would be like some stack of D3 and D5 brains in a non-critical strip background, in the sense that has less dimensions. This is the Worset CFT before taking into account the back reaction of the brains. And then the gravitational dual is like this back-reacted subcritical background that, well, Andrea and collaborators, Leonardo, they have studied more detail in this recent paper. Okay, so only have 7 geometric dimensions. So this is the last slide. So the point is that we construct interpolating models for all the other theories. And indeed, we saw that all these ones that have the same value of alpha, they all come from approaching 2 NS5 brains with different content of the open string sector. Okay, but then the Wick-Coupling limit we are talking about would be like the tensionless limit of this non-critical string background. And the others, they come from approaching 3 NS5 brains. That's what distinguishes them, with different content of the brains and orientiforce. And therefore, this Wick-Coupling limit with this other value of the exponential rate corresponds to the tensionless limit of this other string background. And these are just, so it's for me surprising that you start with this full classification purely from CFT, and you just get that they just come like the closed string background, they are dual. It just comes from this simple stack, a system of approaching these NS5 brains, and that's it. Okay, so let me flash the conclusion. So the distance conjecture seems to be some universal property of conformal manifolds, even beyond Einstein. We started some classification of the infinite distance limit corresponding to these tensionless string limits of critical and non-critical backgrounds. In this case, there are only 3, which now we can understand where they come from. And of course, you can imagine the next step is to go beyond this mini landscape and start considering more than one gauge factor. So thank you for your attention.
You mentioned that these operators saturate the unitarity bound, but from your examples, these are operators, in fact, that are marginal. Why do you use this?
No, the marginal, so you have the marginal operators for the conformal manifold, but then you have higher spin operators that the anomalous dimension depends on the marginal coupling.
I agree, but what I'm trying to say, if you take a scalar, when it becomes massless in the bulk, eventually it's a boundary marginal operator, not an operator of dimension 1, which is the unitarity bound. That's why I'm confused.
But here are higher spin operators, not the scalar operators. Yeah,
like trace F square are scalars.
Yes, but the operator, so these are different. So it depends. There are several operators involved in this game, no? So of course you have these ones, but then you have higher spin operators just constructed from, taking derivative, right, of the scalars and so on. And then the anomalous dimension depends on the gauge coupling square. And these are the ones that saturate the unitarity bound as the gauge coupling goes to 0.
Yeah. So there is no scalar operator in there.
Here, not exactly. So in 2 dimensions, it's different. Okay, it's 2 dimensions.
In string theory, there are scalar operators, right? When you take these decoupling limits, when the scalars.
You also, so it's different. So you also have, but it's not the ones that become exponential on the distance.
Scalar Kaluza-Klein states.
Yes, but that's the point. So in flat space, we have Kaluza-Klein states. Here in 4D CFTs, it seems that what we always find are not Kaluza-Klein states, but only these higher spin operators. So they are always like weak coupling string limits.
Thank you.
Yeah.
Hi, I have a naive question. Why does it stop at 3 NS5 branes?
Why does it stop at
Why
3? Okay, that's not a naive question. So yeah, when I give you this, like the natural question is, okay, what about if I call it 4 or 5 or 6 or 7, right? The point is that right now I started from the CFT, so I considered theories that only have 1 gauge factor, right? If I have more than 3 NS5 branes, what I'm gonna get when approaching the branes are gonna be CFTs that have more than 1 gauge factor. So right now, yeah, exactly. So my understanding is that this was kind of an artifact of having only 1 gauge factor. And now when we extend the classification to having more than 1 gauge coupling, we are gonna find, yeah, like 3 up to infinity, no, NS5 branes. And the question is, do we only find that, or we will also find something different?
Thank you.
So I guess one natural question is why you're only looking at gauge couplings. I don't know, other interesting.
So the point is that the only known examples of infinite distance limits in 4D CFTs, or like CFTs dimension bigger than 2, correspond to weak coupling limits, that the gauge coupling goes to 0. So here I was trying to do a classification of things that are known, like the landscape of CFTs we know. So that's why I restrict to those ones. But then the question is, okay, can you show that this is the only possibility, no? Or could it be that there is a different infinite distance limit that is not a gauge coupling going to 0? And that's what is left to show, to prove that CFT distance conjecture. Like if one can prove, for instance, that this is the only way to go to infinite distance, to have a weak coupling limit, then we would complete the proof of the conjecture, because then we know what happens in that case, and that's it. There is nothing else. So part of the, when we are trying to prove the conjecture, what we are trying to understand is whether this is the only option or there are other options, no? How to show this and what happens then. But so far there is no example, so it's like, yeah.
And you can also maybe go some intermediate step, right? And say, okay, it's a gauge coupling. So what kind of imprint does this have on the spectrum of higher spin states? And can I show at least that this property is always true rather than directly proving that it's a gauge coupling?
Yeah,
but are there some obvious imprints, or is that hard to see? Like, I guess, do you have only even spins, higher spin currents, something? I don't know. I'm just guessing.
Well, you have the spin 4, you have all of them. It's not, so far we have only studied how the anomalous dimension behaves. You can try to go more details, no? About the trajectory, the radio trajectory. Maybe there is a way to do it. I think...
For example, spin 4, but not spin 3, something like that.
yeah, in all these cases, I mean, you have all the spins in the end. Like you have the no, spin 3 might depend on the case. Yeah, spin 4 or more. Yeah. I'm sure there are more things that can be done. Something that it's more clear is that if it's free, if you have a free sector, for instance, we can show that this free sector necessarily is about a free vector multiple. Like it's really about a gauge coupling going to 0 if we have a superconformal theory. That we can show in general. So if it's free, that's it. So the question is it always at infinite distance, do we always get something free? Or can we have something different?